The next topic we're going to talk about in this video is titrations. Titrations involve you slowly adding a solution that we'll call a titrant to another solution called an analyte. When this reaction is over, you've reached the end point of the titration. Usually an indicator will be added, so we'll be able to see exactly when we are switching from an acidic pH to a basic pH or vice versa. When the moles of acid are equal to the moles of base, you've reached its equivalence point. And here are just some pictures of how you would normally set up a titration. You'd have this long burette where you'd slowly be able to track how much, in this example, OH minus you're adding to the solution. As you see the solutions change color due to the indicator, you know you have reached the end point of the titration. In other words, you might see this actually in a lab where you're seeing how the flask will start to sort of change solution, but once you've completely gone to the end point, the flask will completely change color. The easiest example of a titration problem involves starting with a strong acid or base and reacting it with a strong acid or base. In either case, you're going to start with your initial H plus or OH minus number of moles, whether you're starting with an acid or whether you're starting with a base. Then you might be asked to calculate how many milliliters or liters you'll need to figure out what the equivalence point is. And again, our equivalence point is when we're dealing with the same number of moles of acid and base. During this question, you might have 3 different times you'd be asked to calculate pH. At the beginning, where you really only have excess of whatever you started with, whether that's acid or base. At the equivalence point, where you'd have the same number of moles of acid or base. And then after the equivalence point, where you'd have more acid or base, again, depending on what you start with. As you work through these problems, remember it's critical that when we're doing stoichiometry with conversion factors, you need to be thinking moles. But when you look at pH, you need to be thinking molarity. Let's look at a first example. So here I'm starting with a solution of KOH, and I'm titrating it with acid. So this would be a strong base titrated with a strong acid. What is the pH at the following conditions? So let's go through each of these possibilities. Before any titrant has been added. What that means is all we care about is my initial solution. Since this is a strong base, we don't need to worry about an ice table. It's just going to be the pH of the analyte, meaning I can go ahead and take my hydroxide concentration from my strong base, take the negative log of that to give me a POH. I can subtract from 14 to give me its pH. So since it's a strong base, it's very straightforward. Okay, so now I'm starting to add some titrant. So remember, in the question, I now have a volume and a molarity of base. I now have a volume and molarity of acid, meaning I can go ahead and start to figure out how stoichiometry is going to work here. I would first start with my base using its volume and its molarity to figure out how many moles of OH minus. I've included a conversion factor here for my OH minus. You do not need to keep this here, but I don't want you to forget in case we have one of our group 2 metals with a hydroxide. I then can go ahead and use my volume of my acid to figure out how many moles of acid. Same thing here, I'm not using a polyprotic acid, just a monoprotic, so you don't need to use that conversion in this step, but I don't want you to forget to do that. At this point, I am going to have some moles of acid react with some of my moles of base, right? So what this really becomes is kind of like a limiting reactant problem. So what I would do, I can see that I have an excess of OH minus, so I know that some of my OH minus is going to be lost because I've added H plus to it. I now know how much hydroxide's left over. If I want to convert this to pH though, I need to keep in mind that while my number of moles has changed, my molarity of my new solution has also changed because I have less hydroxide left and I changed the volume. So once you're done with the stoichiometry, then you would then need to recalculate what the molarity is. Again, 25 milliliters from my basic solution, 10 milliliters from my acid solution. I then have a new molarity. I can then calculate pOH, subtract from 14, and then I will get my pH of the solution. Now, let's go to the equivalence point. Here, I know that at the equivalence point, I have to remember the definition that the moles of acid need to equal my moles of base. So if I have the same number of moles and I'm dealing with a strong acid and a strong base, I'm back to where I started with a normal solution. I know my pH is going to be 7. Now, the next question involves 30 milliliters of titrant, which means we are going past the equivalent point. And so you can see here, just by looking at my molarity of my acid and my base here, I'm going to now have switched from having more base to having more acid. That doesn't mean we're going to start off any differently. We're still going to use our volume and molarity of our base to figure out how many moles of hydroxide we have. We're still going to use the volume and molarity of my acid to figure out how many moles of H+ I have. My acid and base are going to react. We can see here from our moles that I now have more acid than base. So I'm going to subtract how much hydroxide that's present. This gives me a new number of moles of my acid. Remember, before we can go to pH, we do need to recalculate the molarity of the solution. And so we would need to use the volume of both the acid solution and the base solution with my remaining acid to get a new molarity. Once I have my molarity of my H+, I can then turn that into pH, and I can get the pH of the solution. One more question with this titration. If I start to add infinity milliliters of titrant, remember that effectively means that my base solution, my 25 milliliters of my base solution, is going to be completely reacted. It's almost going to completely disappear. And as I continue to go higher and higher with milliliters of my acid solution, the solution of my titrant is going to become my solution. And so I know that if I can calculate the pH of my titrant, it's going to be the same as my pH of solution, meaning I can just take the log of the solution concentration to get the pH. The other more complicated example of titrations involved weak and strong. And so I'm going to set up some guidelines for a weak acid with a strong base. But notice a lot of the things we're talking about, instead of talking about conjugate bases versus conjugate acid, a lot of the things are going to stay the same. So there's going to be 5 special areas that you're going to look at as far as where you might be asked to calculate pH. The first one is, the first big difference is that, remember, in the last example we were dealing with strong acids and strong bases. We didn't have to worry about dissociation. And so in this example, if we're starting with a weak acid, in order to figure out what the initial pH is, we're going to need to use the Ka with an ice table. So that adds some time to this first step. Before the equivalence point, remember my strong base is reacting with pieces of my weak acid, meaning that I'll be able to use my Henderson-Hasselbalch equation because I will have created a buffer region. When I get to the half equivalence point, and that sounds exactly like what it is, the equivalence point is when the moles are equal. The half equivalence point is when I have half as many moles as what I'm starting with. That's going to be equal to the pKa, and we'll talk about how that works in a little bit. When you get to the equivalence point, this means that all of your weak acid is completely gone, but as a result of that, you are going to have its conjugate base be present. And so at your equivalence point, you'll then need to start using the Kb of the conjugate base with an ice table. And then after your equivalence point, meaning all of my weak acid and all of my weak base is essentially gone, I will have more strong base, meaning I can easily calculate the pH based off of my hydroxide concentration. Reminder again here, when we're doing stoichiometry, it's in moles. When we're doing pH, it needs to be in molarity. So notice this question is written pretty much like the last example. The only difference is I've changed my starting point to be a weak acid instead of a strong acid, and I still have a strong base. Let's go ahead and see how this example works. Before any titrant has been added, I essentially have a weak acid solution. So we've already talked about how to calculate pH of those solutions, but this will be a review. I would go ahead and write my reaction of my acetic acid with water, making its conjugate base, the acetate ion, and the hydronium ion. I would then need to set up an ice table with the molarity of my acetic acid. I know at time initial or time 0, I know that I have 0 molarity of both my conjugate base and my hydronium ion. Since I have zeros on my product side, I'm going to be decreasing from my reactant side and increasing from my product. My equilibrium rho will just be the sum of both of those. And since my Ka is smaller than 10 to the negative fourth, I know that I can use my approximation here. Make sure we're writing that it's smaller than 0.1. From here, I can then set up my equilibrium expression. And if we do the math here, I'm going to get X equal to 0.00134 molar. I would then, before I can just get the pH of that, I would need to go back and check to make sure my approximation works. I get a Ka that's close to my value from the question. I can then go ahead and use my hydronium concentration and get my negative log of that to get my pH of my acidic solution before I have added any of the strong base. Now I've added some base to this. So this is going to feel like a buffer question because I don't have any of its conjugate base present, but by adding base to it, I'm going to make some. In order to figure out how many moles are remaining, I will need to use stoichiometry. So here I'm using the 2 milliliters of my base to figure out how many moles of hydroxide I have. I'm going to use the 25 milliliters of my acetic acid to figure out how many moles of acetic acid I have. And so at this point, I know that my base is going to react with my acetic acid, thereby creating some of the acetate ion. So I can see that I have more acid than base present. I can take my moles of acid, subtract my moles of hydroxide that I've added. This is telling me how much moles of acid that I have left. I have 0 moles of my conjugate base present through the part of this red hydroxide with my blue acid. I have now made some of my conjugate base to give me concentrations of both moles of my weak acetic acid and moles of my weak conjugate base, meaning I am in the buffer range. Once I've had my moles of acid and base, I can go ahead and use Henderson-Hasselbalch. So I can take the negative log of the Ka. This is a weak acid. I already have Ka given. I can go ahead and put in my moles of base over my moles of acid. and it'll give me my pH of 3.66. Now I expect this to be higher than my last part of the question because I've added base, so my pH should be a little higher. Now what about at the half equivalence point? Now I know that I'm starting with this many moles of acetic acid, and my equivalence point would mean that I'd have the exact same amount of base. But at my half equivalence point, it means I only am going to have half as much base added. So I will still be able to react my hydroxide with my moles of acetic acid, but I'll be able to subtract half of it. And you'll notice here that I'll have half of my acid remaining, thereby meaning half of my original acetic acid turned into its conjugate base. And now you can hopefully see why we're going. And I told you our general rule is at its half equivalence point, my pH is going to be equal to the pKa. So you won't need to do these calculations, but you're going to be able to see about why that relationship works. So I have my moles of acid, I have my moles of base. They are conjugate and weak of each other, so I can use Henderson-Hasselbalch, meaning I can go ahead, calculate my pKa, same number as before. I can put in my base and acid, but if we look at this, the inside of my log is going to cancel because it's going to be equal to 1. The log of 1 is 0, meaning my pH will just be equal to my pKa. So something to help save you time to remember at the half equivalence point when you're doing a weak acid or base with a strong acid or base, your pH is going to be equal to a pKa, but if you go in and do the work, you'll be able to see that that should be the case. Again, I've added more base, meaning my pH should continue to go higher. Now I am at the equivalence point. So I know that I'm still going to have to figure out how many moles of my acid are there, right? So you'll still have the same number for all these calculations. I know that my equivalence point is going to give me the same number of moles of base, meaning I can go ahead and have all of my base react with my acetic acid, meaning I'll have 0 moles of my acid left. But by looking at this reaction, we have generated some of my purple conjugate base, meaning the only thing that's present is moles of my conjugate base. So we are no longer in the buffer region, but now what we will have to do in order to figure out pH, we'll have to use my moles of base. However, it is a weak base. So in the case of our strong titrations, we were able to just either calculate pH or pOH. Now, if I know how many moles of a weak base I have, I'm going to again need to use an ice table. So I know that I'm going to need to set up an ice table involving my conjugate base. In order to do that, I'm going to need 2 pieces of information. The first thing I'm going to need to do is figure out what is my new molarity. And so I'm going to need to know if I'm at the equivalence point and I know how many moles of hydroxide I have, I need to know how much volume I needed to get there. So I also know that since I have the same number of moles of my conjugate base as I do of my hydroxide, I can get a new molarity. In addition, remember, this is a weak base, but the only information from the question I got was its Ka. So I'm going to need to use Kw to get to my Kb. So I know what the Kb of my weak base is. I now have the molarity. I can go ahead and write my reaction standard base template with my acetate ion reacting with water, yielding my acetic acid and hydroxide. I can go ahead and create my ice table. I have my concentration of my weak base. I know that I have 0 molarity of both my acetic acid and my hydroxide. I'm increasing, going towards the products. I know that because my KB is so small, I can try to use my approximation. And at this point, what I would have would be my KB expression. I have my two unknowns up top. I can get a value to solve for my hydroxide concentration. Before I can use this to get POH, I do need to check to make sure this is accurate. This is pretty close to my original KB that I used in the question. So I can go ahead, take the negative log of my concentration to give me my POH and subtract from my pH, or subtract to get pH. Now remember, why we need to do this step is because there is no hydroxide remaining. If I had hydroxide remaining, this would be much easier, and this would be negligent. What if I continue to add titrant and I've added 30 milliliters? Well, now I not only am going to react all of my acid, I'm going to have some remaining hydroxide. So this one will be a little bit more straightforward because since we're dealing with a strong base, we don't have to worry about doing an ice table. We'll still start this the same way, but now that we're past the equivalence point, it means base is going to be favored. I still will need to get my concentrations of my moles of acetic acid. I still will need to figure out how many moles of OH minus I have. I can see that I have more OH minus than I have acid, so I know that I'm going to subtract the smaller number. This now tells me how many moles of base I have left. Here's the end of the stoichiometry piece. I now need to get from moles to pH, meaning I'll need to figure out my new molarity. So I'm going to add the 25 milliliters and the 30 milliliters together. I now have a concentration of just the hydroxide. I can use my log relationship, turn that into a POH to subtract from 14 to get my new pH of the solution. Again, I can see this continues to increase as I've added more solution. In the last example, we talked about having infinity amounts of titrant. The same thing is going to happen here. So eventually, my small amount of acid is going to be overpowered by infinity amounts of milliliters of titrant. So I can say that at time infinity, or at concentration infinity, I will have my pH of the solution only equaling my pH of titrant. So I can take the negative log of my hydroxide concentration to get POH, and you can see that here we are at a pH of 13. The reason why this isn't all the way at 14 is because we do not have my 0.1 molar. We're really close. Here's a very similar question. Notice the key difference is I'm asking you to start with a weak base instead of a weak acid. So this is a weak base titrated with a strong acid. Go ahead and pause the video now and try this one on your own. Okay, so to start this problem, I see that I'm going to have a weak base, a pyridine. And so before any titrant has been added, it's just going to be a weak base question. I can go ahead and write my reaction. So pyridine plus water is going to give me my conjugate acid plus hydroxide. And I can set up my table. I have my molarity. I know that at the beginning I should have relatively 0 of my conjugate acid and hydroxide. I can fill in my table. My KB is 1.5 times 10 to the negative 9th, small enough for me to try to use my approximation. And I can go ahead and set my KB equilibrium expression. Remember, products over reactants. I can put in my terms, cross multiply, take the square root, and that should give me a number of about 1.01 times 10 to the negative 5th molar. Now, before I can go ahead and put that into my POH expression, I do need to check to make sure my approximation is valid. I'll do that by putting in my term for both of my numerators, and I get a KB that's very close to my original value, so the approximation will work here. Then I can put it into my POH formula, get a value for POH, and then subtract from 14 in order to get my pH. So at the beginning, straightforward, weak base problem. Now I've started to add some titrant, so we're going to have to use stoichiometry in order to do this one. I'll start by using my volume of my acid and molarity to figure out how many moles of H+ I'll have. I'll also can use my volume and molarity of my base in order to figure out how many moles of my base I'll have. I'll have a one-to-one reaction, so here I'll take some of my acid until it's completely gone. I'll decrease my amount of my pyridine while increasing the amount of my conjugate acid. I know that all of my H+ is going to react, giving me a small amount of my base left over. The exact same amount of my acid that was used is going to be how much my conjugate acid is now remaining. I have a weak acid and a weak base, meaning I can use the Henderson-Hasselbalch equation. I have my concentrations. I need to use Henderson-Hasselbalch. Remember, this was a weak base question, so I'll need to convert that to my Ka if I want to use the Henderson-Hasselbalch form. Once I have the Ka, I can get a pKa and insert my moles of base, my moles of acid, and I should get a pH of around 4.67. Again, I added acid here to the solution, so I should see my pH going down. At the half equivalence point, I know how many moles of pyridine I have from the previous part, but I put it up here again. At the half equivalence point, I'm going to have half as many moles as I would see at the equivalence point, so I'm going to have half as many moles of acid added. I'm still going to have my base combined with my acid, and remember, at my half equivalence point, I'm going to have a mixture of a conjugate acid and a weak base, and they'll be the same. So at the half equivalence point, it will be equal to its pKa. We can keep going with this. Put in your Ka, which we have from the last question, and we'll see that it cancels. And so again, at your half equivalence point, your pH is equal to your pKa. Less acid than we added in the last one. In that last example, we actually went past the half equivalence point, so we should see pH going a little higher. At the equivalence point, I'm going to have the same number of moles of acid as I have as base. So that means I'm going to add 0.0017 moles of HCl. Remember my reaction. If I'm at the equivalence point, it means my moles of base and my moles of acid that I've added will now completely neutralize itself, but in the process making more of my purple conjugate acid, meaning I now have a weak acid problem. So weak acid problem, I'm going to need to go through the ice table. In order to get to my ice table, I need molarity, so I'll again calculate how many milliliters it took to give me the equivalent amount of moles. I can now take the moles of my conjugate acid over the liters of my original base solution, as well as the amount of acid I've added to get my molarity. I'll need to use my Ka in order to use my ice table. I can go ahead and put in my molarities. I know that we're going to be going towards the product, so I'll see that my X's are increased on the product side, decreased. I can see from my Ka that we are small enough so that we can use the approximation. And now we will go to set up my equilibrium expression. After completing my table, I can set up my equilibrium expression. Remember, I have my Ka from the previous slide. I'm going to solve for my x value, right? So cross multiply, take the square root. That gives me my hydronium concentration. Before I can check that, I need to make sure my approximation is valid. When I do that, I get a value of 6.8 times 10 to the negative 6th, close enough to my Ka. I can go ahead. When I take the negative log of my concentration, I get a pH of 3.26. Now I'm adding 20 milliliters. Again, you can see that based off the concentration, I'm going to have an excess of acid. So I'll still go ahead and use my molarity of pyridine and my volume to get how many moles, same number we've had for the previous parts of the question. I then will figure out how many moles of acid I've actually added. At this point, you can verify that we have more acid than base. So in this case, I'm going to use up all of my pyridine. How much hydronium I'll have left, or how much acid I'll have left, will be 0.0009 moles. I can then get a molarity of my hydronium concentration in order to figure out pH. Again, remember the difference between going from moles to molarity in order to figure out what the pH is. So I'll add my 25 and 20 milliliters. I now have a molarity of my solution. With the molarity, I can take the negative log and turn that into pH. And notice here, we've added a lot of extra acid. We have an excess of it. We should start to see a pH that's very acidic. The last part, once we have an infinity amount of a titrant, we know that that's just going to be essentially the solution. So the pH of my solution is going to be equal to the pH of the titrant. What I'm going to have an excess at the end, so I can go ahead and take the negative log in order to see what my pH is. Here we're seeing it go less than 1 because we have a higher concentration than my 0.1 molar. That wraps up buffers and titrations.